Okay, Chemistry 3101. Where we left off last class, last Thursday, was looking at question 7.75. And it says we're taking this substrate. So this alkyl halide right here, just to review. And we said we're treating it with sodium methoxide. Well, sodium methoxide is a strong base and it's a strong nucleophile. And so we're asked to provide the all products, and then we're going to identify the major product. Well, when you have a secondary alkyl halide, so you can see here that this is a secondary alkyl halide, we only have one kind of beta proton. Well, first of all, if it's secondary, we know that SN2 is going to predominate. And so we get the SN2 product, and that's what I wrote here. And of course, remember that when you do an SN2 on a stereocenter, we get inversion of configuration. But we know that is actually going to be the minor product. So we can put here the SN2 product is the minor product because it's the E2 product that is going to predominate. So what I said is, what you need to do is you need to draw a Newman projection going down this carbon-carbon bond that I have highlighted in yellow, and I started to do that last class. Okay, I started it, but I didn't finish it and decide whether the product was E or Z. So if you completed that Newman projection, which I know you all did, you end up with your bromine on the right-hand side, your proton here, your beta proton is on the right-hand side as well, and then you have your methyl group over here. This is just a CH3 group. I'll just leave it like that as a bond line structure. So what I'm going to do is I'm going to rotate it so that this proton is going to be in this position so that it will be anti-periplanar to the bromine. So let me go ahead and do that. So I'll redraw my Newman projection. So it's going to look something like this. So I didn't touch the ethyl group in the back. I left that there. I still have my phenyl. Sorry, I don't have my phenyl coming straight down, do I? Sorry, I'm not doing this correct. So let's see here. I've got my methyl group going straight up. I've got my ethyl group that's going to be down here. That's better. And then I have my proton over here. There we go. I've got my leaving group here. I didn't touch this. And of course, there we go. I do have my phenyl going straight down like that. So now you can see that the beta proton, this is the beta proton, and this is our leaving group. You can see that they are all in the same plane, therefore they are anti-periplanar to each other. Now, yes, the mechanism, which it doesn't ask you to draw, the mechanism is what? It's going to be abstract the proton, form the double bond, lose the leaving group, okay? So when we do that, we end up with an alkene. We just need to decide, is it an E alkene or a Z alkene? So let's see here. So we're going to have our double bond. Okay, and then I'm going to put my phenyl group over here like this. So on the carbon that has the phenyl group, I also have a proton. So I've got a proton up here, not necessary to draw it in, but you see that the ethyl group ends up on the same side as the phenyl. So now I've got my ethyl group over here, and you see that the methyl group ends up on the same side as the proton, like that. Could anybody tell me that this product here, would this be the E product or the Z product? And it's not a trick question. Would that be zusammen or entgegen? Anybody for this one? It's going to be the Z product. Exactly. Thanks, Jenny. Yeah, this is the Z product, right? Because the phenyl takes precedence, and then the ethyl takes precedence. And so this is the Z alkene, and this is the major product of the reaction. Okay, so two products in this reaction, but the Z product, the Z alkene, is the major product. Why? Because it's actually the E2 mechanism that predominates when we have a secondary alkyl halide and a strong base, a strong nucleophile. Well, let's move on from there, and let's take a look at 7.75 G. So 7.75 G, we have this compound, and it's always kind of fun to practice your nomenclature along the way. So this would be what? 3-bromo-3-methylpentane, and we're treating it with potassium T-butoxide. So T-butoxide, which we know is a strong base, but it's a terrible nucleophile. Why? Because it's too big and bulky. So we'll just put here strong base, and we could just put here weak nucleophile. It's fine. Weak nucleophile. Okay, so this is never going to do any kind of substitution reaction because we have a tertiary alkyl halide. So what's the only possibility? The only possibility here is going to be an E2 reaction. But you notice that we have two types of beta protons. We have the ones on the methyl group here, And then we also have the ones on these methylenes here. If you're still struggling to recognize where's the beta proton, remember the carbon that the halogen is attached to, that is the alpha carbon. One carbon away, that's a beta carbon, right? So this would be a beta carbon. Oops, come on, red pen. This would be a beta carbon. This would be a beta carbon. And if you're saying, well, what about this one, Mr. Dion? Isn't that a beta carbon? It is. However, it's identical to the one in blue. So there's no need to put that down twice. So let's write down the two products that we're going to get, whether we abstract the proton in red or the proton in blue. So we're going to start with the proton in red. Why am I going to start with that one? Well, it's kind of just an arbitrary choice, but it is going to give me the major product. How do I know that this is going to be the major product? It's because I have a hindered base, right? It's a strong base, but it is hindered. And so the major product is going to be the less substituted alkene. And you see that if I abstract the blue proton, what I end up with is this. This is going to be I'll just leave it as just the major. That's going to be a minor product. All right, because again, we have a hindered base. Could anybody tell me there's one thing that's missing here? There's one more alkene that I should draw here. Could anybody identify what that would be? So this is a good place to start. We've got 2 out of 3, but there's one more alkene that's missing here. So this would be an E alkene. This is E, or you could call it cis, either way. But exactly, we need to switch it, don't we? Okay, we need to draw the Z alkene as well. So we would have to draw something that looks like this, where we have the 2 methyl groups trans to each other, like that. There we go. So that's going to be another product. So this would be a Z, or this is going to be a trans product, right? But these are 2 different products. These 2 compounds are diastereomers, aren't they? And so we end up with actually a total of 3 different compounds in this case. Now, between these 2, which one is going to predominate? I guess that this one would be in a greater quantity. Why? Because there's less steric hindrance between the 2 methyl groups than there would be between here. But it's not asking us for any of that. Okay, it just asks us to identify the major product. And so we're good with that. All right, let's move on to the next problem, which is in a very similar vein to this problem. In fact, I'm just going to copy and paste some of it, because in H, what we're going to do is, let me just see here. So I'm going to copy this part here and I'll modify it a little bit, because all we're doing is taking the same substrate and we're changing the base. Okay, so now we're going to change it to sodium methoxide. So I'll put here sodium, what is it? Sodium methoxide. So let me write it over here. Sodium methoxide, which is a strong base and a strong nucleophile. Strong nucleophile, like that. All right. However, since we have a tertiary alkyl halide, we're not going to get any substitution whatsoever. It's not going to happen. And so you can just take the SN2 and you can just cross that off completely. It's not going to happen. And again, it's because our substrate is tertiary. So we're going to get the exact same alkenes that we did before. So I'm just going to scribble them down here instead of copying and pasting them. Here is the Hoffman product. Here's one of the Zaitsev products, and the other one is this compound. There we go. So we end up with these 3 compounds. Now, since now we're dealing with an unhindered base, so unhindered, the more substituted alkene is going to predominate. Both of these are tri-substituted alkenes, but remember, based off of what we said in the last problem, that there's going to be less steric hindrance with this one than there would be with this one. And so the major product is actually going to be this product. So we'll put here major product. And that's all we're asked to identify. And again, this compound is an E product, but it's also a cis product. All right, there we go. Give me a thumbs up if you're with me on the difference between these 2. The T-butoxide is a hindered base. The sodium methoxide, unhindered base. So we end up with a different ratio. Yeah, okay, awesome, cool. Great, and stop me if you have a question, okay? These are important. The next one, let's see here, HI, let's see here, I did this one, yep. So this is 7.75, 7.75. I, come on, it's an I. There we go. So we end up with this compound here. So we have a stereocenter. Nope, I drew my stereocenter wrong. It's on a dash. So this compound would be what? This would be S2-chlorobutane. That's what you would call this compound. And we're treating it with sodium hydroxide, NaOH. Well, we definitely know that sodium hydroxide is a strong base. You guys all studied general chemistry long enough to know that. You know it's a strong nucleophile. Strong nucleophile. And we're starting it with a secondary alkyl halide. Now, in this case, the E2 is going to predominate, but we are going to get some SN2 as well. Now, if it's SN2, we're going to get inversion of configuration. So I'm going to draw the SN2 product first. Even though it's a minor product, I'm just going to draw it first because it's really quick to draw. Now, in terms of the alkenes that we can form, there's actually a total of 3 possible. Sorry, go ahead. Oh, okay. Did somebody have a question? Okay, all right. All right, so with this one, so we have a total of 2 types of beta protons. We have this one here, we have this one here. And so there's at least 2 alkenes. There's actually more than that, but let's draw them out here. If I was to pull off the proton in red, I'm going to end up with this alkene. If I pull off the proton in blue, I'm going to end up with this alkene, the trans, but I'm also going to end up with the cis. Okay, so I actually end up with a total of 4 products, but when it comes to the major pathway, remember E2 is going to be the major pathway when you have a secondary alkyl halide. And so since we have an unhindered base, right, hydroxide, I forget to write it down here, unhindered, that means that the Zaitsev products, or the more substituted alkenes, are going to predominate, but the trans product is less sterically hindered, and so this is going to be my major product. All right. So if you just take a systematic approach to it, you see how it's not that bad when you take just kind of a step-by-step approach to solving these problems. Let's take a look at 7.75J. So this is J, one of my favorite reactions. Why? Because it's easy to set up. Okay, not easy to figure out what the products are, but easy to set up in the lab. You just take this alcohol and you just heat it up with sulfuric acid. I mean, as far as cooking goes, I mean, it's about as simple as you can get, right? Take a strong acid, put your alcohol in, and turn on the heat and let it stir, okay? Now remember, with this kind of reaction, what's going to happen is you're going to remove water. So we're going to have loss of H2O, okay? You could write it like that, or sometimes we just write negative H2O, okay? Which means we're losing water. So that means we're going to make an alkene. Now, hopefully you remember that when we do this reaction, the most substituted alkene is going to be the major product. Now, we're going to get all the regioisomers. So that means we're going to have this compound. We're going to have this compound, which is the most substituted. We're also going to have this compound. Okay, so we're going to have all 3 of these compounds. But which one is going to be the major? Remember, it's the most substituted alkene that is going to be the major product in this case, okay? And if you're asking me, are you telling me that every time I heat up an alcohol with concentrated sulfuric acid to remove water, that the most substituted alkene is always going to be the major product? Yes. In this specific reaction, yes. So we'll put here most substituted alkene. All right, you see that this alkene is tri-substituted. This one is di and this one is mono. But if you're wondering, if there were 2 diastereomers here, you would just go with the one that's less sterically hindered. That would be the major product in that case. All right, let's try 7.75K. I'm going to squeeze it on here. So this is 7.75K. This is a good question. I've asked this on a quiz before, this exact question. So remember what OTS is, okay? So OTS, that's a tosylate, which is a good leaving group, good leaving group. Remember that making a tosylate is a way to convert an alcohol which is a crummy leaving group, into something that is a good leaving group. And so we're going to treat this with sodium chloride. You might think salt, like table salt, that's pretty boring. Well, let's think about this, okay? Chloride itself is not a strong base. It's a crappy base because it's the conjugate base of hydrochloric acid, which is a strong acid, but it is a good nucleophile. So we'll put here good nucleophile, good, or you could put strong nucleophile is fine. Let's put strong. I think it's the way it says it on in our textbook. So strong nucleophile, but yes, it is a weak base. So we're not going to get any elimination in this case. And we're starting it with a secondary alkyl halide. And so the only thing that's going to happen here is an SN2. Now, if you don't remember what DMSO is, that stands for dimethyl sulfoxide. It is a polar aprotic solvent. And if you remember, the aprotic solvents are going to promote an SN2 reaction. So this is just a way to make this reaction go even faster. Now remember, when you do an SN2, you're going to get inversion of configuration. So this methyl group that's on the wedge, it's going to be on a dash when we're done. So let's write down what the product is going to look like. So we've got our chloride here. There you go. So remember, we are going to have inversion of configuration because of backside attack, right? We flip the stereochemistry when we do that SN2 reaction. So I'll just write down here SN2. Okie doke. All right. The next question is actually a little bit faster. It's question 7.76, but it's very pertinent because it just asks for major products only. So it's not like a lightning round, but it is a little faster when we just have to concentrate on major products only. So major products only, okay? In those standardized exams like ACS and MCAT and DAT, they like to ask these questions. They do have the questions where it's like, what are all the products, or what's the minor product? They'll do that too, but they like to ask questions where it's like, just give me the major product. That's it. So let's do these ones a little bit faster. So if we start out with this, come on, this stereocenter here. So this would be what, R2-chloro butane. We treat that with the sulfhydryl ion. So this is sodium hydrosulfide, like this, okay? So remember, the SH minus ion is a, let me move this down here. It is a weak base, but it's a good nucleophile. So we'll put down here, weak base, but strong nucleophile. And we have a secondary alkyl halide. So what's going to predominate here? The predominant mechanism is going to be an SN2. In fact, it's the only thing that's going to happen. So we're going to get inversion of configuration. And so we invert our stereocenter. And remember, this functional group here, this is called a thiol. Okay, when you have SH, it's a thiol. OH is an alcohol, SH is a thiol. There we go. All right, so finish that one. Let's try B. In B, we're starting it with this. So this would be what? 1-bromobutane, and we're treating it with DBN. So diazobicyclononane. And remember that this is a strong base, but like the worst nucleophile in the universe. So here, weak nucleophile, or if you want to write down worst nucleophile in the universe, that's fine too. I'm being a little bit silly here, but the only thing that's going to happen here is an E2 reaction, right? Nothing else can happen. Well, if this is my alpha carbon here, that means this is my beta carbon. Does it have a proton on it? Absolutely. So what's going to happen is the DBN is going to pick up that proton. You're going to form the double bond, lose the leaving group, and you're going to end up with this compound here. This is called 1-butene. We'll take a look at alkene nomenclature in chapter 8. But there we go. The only mechanism in that case is going to be an E2. So let's see here. This is 7.76C. We're starting it with a tertiary alkyl halide right here, and we're going to treat it with sodium hydroxide. Oops. Sodium hydroxide in water, right? Okay, well, we know that sodium hydroxide is a strong base, and it is also a strong nucleophile, but we're not going to get any nucleophilic substitution here because we have a tertiary alkyl halide. And so what's going to predominate here? what's going to predominate here is going to be E2. In fact, it's going to be the only thing that can happen. So let's see here. We've got two types of beta protons. We have this type in red, and we have this type in blue. Could anybody tell me, and it's not a trick question, which one would be preferentially abstracted to make the alkene? Would it be the red or the blue in this case with sodium hydroxide? Would it be the red proton that gets ripped off to make an alkene? Or the blue? Because we're just looking for the major product here. Thanks, Rubio. Exactly. Thanks, Lauren. Exactly. It's going to be the blue. Why? Because it's an unhindered base. Unhindered base. So it's going to pull off the one in blue. And we're going to end up with this compound. This would be called 1-methylcyclohexene. All righty. There we go. Not too bad. Let's keep going. So remember, we're just looking for the major products here. Okay. Let's try D. I can't even read my own handwriting. Okay, let's see here. We have another tertiary alkyl halide. So now we're going to treat it with water. Okay, water, and we're going to heat that. Now remember, water is a weak base, and it is a weak nucleophile. Okay, weak base and weak nucleophile. So if you look at the chart that's in our textbook, when it has weak base, so if it has weak base, weak nucleophile, and then it has tertiary alkyl halide, okay, it actually splits it down the middle. It says SN1 and E1. It says 50-50. So let's draw both of the products. So the product of the SN1 would be this. So we replace the bromine with a hydroxyl. So this is, again, this is the SN1 product. This is what we call the solvolysis reaction, or the solvolysis product. And then the E1 product would be this one here, okay? Okay, this is the E1 product. Now, we do have to make a choice here about which one is the major product. Now, if you remember, I mentioned this when we went over SN1 and E1. Now, I can't remember exactly the way they put it in the textbook, but we looked at the reaction coordinate diagram, and it had potential energy, and it had the reaction coordinate like this. So it had something that went like this, okay? And then, another pathway that went like this or something like that. And what it said is that one of them was lower in energy. So I think the way that they put it is they said the E1 or the elimination products were actually higher in energy, and that the SN1 was lower in energy. So you might think, well, then that means this is going to be the major product. Hold the phone. What I told you is if the elimination products gives you a mono or di-substituted alkene, they're going to be higher in energy than the SN1. If the the elimination products, so these are also elimination products, if it's tri or tetra substituted, it's going to be lower in energy than the SN1. And this one happens to be tri-substituted. And so it turns out that this is actually the major product. Okay, so the major product. I can't remember this coming up on a final exam or anything like that, but it is pertinent, okay, that the elimination products, when they're mono or di substituted, they're going to be less stable than the SN1 product. But if they're tri or tetra substituted, they're going to be more stable than the SN1. I think it's reasonable to know this. The reason why is because when you're dealing with the weak base, weak nucleophile, they don't even react with primary and secondary. And so there's nothing to even know for those reactions, right? If you look at the table, there's just two big X's there. So this is the only one. So you could even make a note of this. You could just say E1, you could say mono / di versus tri / tetra. Okay, tetra. And you could put SN1 in the middle or something like that, okay? Anyhow, there you go. So that solves that one. So 7.76E, 7.76E looks a little something like this. So we have a secondary alkyl halide. Authors really hung up on these secondary alkyl halides anyhow. So we get the secondary alkyl iodide, We're treating it with a big old bulky base of potassium T-butoxide, which is a strong base. We'll hear weak or terrible nucleophile. So we're not going to get any substitution in this case. The only thing we're going to get is going to be E2. Now there's two types of beta protons. There's the one in red and there's the one in blue. And this is not a trick question whatsoever. Could anybody tell me which one of these is going to be preferentially pulled off by this big bulky base? Thanks, Jenny. Absolutely. It's going to be the one in red. Thank you very much. So the major product is going to be this alkene. There you go. So that's going to be the major product of the reaction. Okay, we've got a couple more and then we're done with this one. Let's see here, 7.76F. So 7.76F. We're starting it with another tertiary alkyl halide. So this will be what? 2-bromo, 2-methyl pentane. We're treating it with sodium methoxide. The sodium methoxide. And they gave us a solvent, which is neither here nor there, but we have a tertiary alkyl halide. Remember that methoxide is a strong base. It's also a strong nucleophile, but we have a tertiary alkyl halide here, and so the elimination mechanism is going to predominate here. We've got two types of, we got two types of beta protons. We have this one here, and then we also have this one here in black. Since we have an unhindered base, the predominant mechanism is going to be the one where it pulls off the proton in black that I have there. And so the major product is going to be this. Oops, that's not very pretty. There we go. All right, so this is going to be the major product of the reaction, which is the Zaitsev product, like that. And then for G, 7.76G, we get this interesting looking compound here. So there we go. We've got 2-methyl. So this would be what? 2-bromo, 2,4,4-trimethylpentane. And we're treating that with potassium T-butoxide. And we know that is a strong base. Worst nucleophile ever. No, I'm going to put here weak nucleophile. Weak nucleophile. This is tertiary. It's definitely the E2 mechanism that's going to predominate. But we know that it is a highly hindered base. And so in terms of beta protons here, there's two types. We have the type in red, and then we also have this type here in blue. The one in blue is going to be, the one in red is going to be ripped off predominantly because it's a hindered base. And so our final product, 1, 2, 3, 4, 5, is going to be, that's not pretty. It's going to be something that's worse. Oh, sometimes I find the iPad really hard to draw with. There we go. That's maybe a little better. And there you have it. So that's going to be the major product. And of course, this is the Hoffman product. The Hoffman product. So those are a little faster when you're just asked to determine the major product, right? Maybe a little less thought involved, but anyhow, there you go. So a little bit about that. And remember, make sure you're able to do questions like 7.75, or you're asked to assess, what is going to be, or show me all the products that can be formed there. Very important to be able to solve those types of problems.